Hello. Today we're going to consider the definition of a limit. What do we mean by a limit? And we're going to approach this in a mathematical way. And what I mean by that is, typically in a calculus class you don't get the real definition, the real mathematical definition, until after you've already played with limits kind of by intuition in some respects. And we're going to do this like a real math class in terms of, we're going to get the definition first because that's mathematically more precise. And so, the limit as x approaches a of f of x equals L, this is notation here. So I'm saying what happens as my x value approaches a, for the function f of x, this limit is L, means, this is my definition, for any epsilon greater than 0, there exists some delta greater than 0, such that S dot T dot is such that the absolute value of f of x minus L is less than epsilon for all x satisfying. 0 is less than the absolute value of x minus a is less than delta. I'm going to write an alternate way of writing this. It means, the first part obviously is the same. For any epsilon greater than 0, there exists delta greater than 0, that part's the same, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. This is written as an if-then statement. This is kind of how we generally think of it. Now, what does all this mean? Well, the idea is, intuitively, if I have some function f of x and some value a, x equals a, and what this says is that clearly in this particular circumstance I want my limit value to be that value here, but again, we don't actually have to have a point on the graph. We could have an open circle here and the limit would still be the same. But what this is saying is that if I put an interval around L of epsilon width, well, 2 epsilon width, but epsilon in either direction, so in this case, this distance from L, this would be L minus epsilon, this is L plus epsilon. Then there exists some delta down here, which let me extend this down. There exists some delta down here so that if I look at any value x that is a delta's distance, this would be a minus delta, this is a plus delta. Any value x here will map to some functional value there, which is within the interval, epsilon interval over there. So it's kind of somewhat convoluted in some respects, but this is what we have to do in order to be precise mathematically. Given any epsilon interval here, there's a delta interval here, so that if my x value is in the delta interval here, then my y value is within the epsilon interval there. Now a couple things. The 0 less than absolute value of x minus a, this just means that x is not equal to a. So again, with all of these, we want to, it's called a deleted neighborhood, but we want to get close to a, but we don't actually get to a. We don't care what happens at x equal a. The whole idea of a limit is to predict what happens as we get close to it. What should occur. It doesn't matter what actually does occur. We don't care at all what actually occurs. So that's all the 0 less than part of it means. But this is kind of what's going on. Another way of looking at this, kind of let's break up the two dimensions. And boy, that's not very good. Let's think of this as my domain. And we have my value a here. And we'll think of this as my codomain, my y's, and I have my value L here. And what this says is that if I put an epsilon interval around L, this is again is L minus epsilon to L plus epsilon, that there exists a delta interval around A minus delta, A plus delta, such that any x within this delta interval, again we exclude A itself, but any x within this delta interval maps to some y value within this epsilon interval. And clearly, what's going on here is that if I start with a smaller epsilon interval, then that means I would need to have a smaller delta interval. But the point is that if, no matter what interval, epsilon interval I pick, this is always true, then basically we can get this shrunk down as close as we want. Which means that as I approach A here, my y value has to approach L over here, which is what we were looking at in terms of limits. So this is the precise mathematical definition. Now, we can use that to kind of deal with some, let's kind of see this in a different way. Suppose I want to find the largest value of delta so that f of x is equal to x squared, the absolute value of the absolute value of f of x minus 4 is less than 0.01 when the absolute value of x minus 2 is less than delta. So I'm giving you an epsilon here. And, oops, f of x minus 4, shouldn't be L. And I'm giving you an epsilon. I'm saying what's the largest value of delta that will work in this particular case. So we're kind of revisiting what we had before. This is my 0.24. And I'm saying let's put an interval of 0.01 around 4 and find the largest possible interval that will work around 2. And this is pretty simple. We just basically have to work backwards. And so we would say that the absolute value of x squared minus 4 is less than 0.01, which would mean negative 0.01 is less than x squared minus 4. is less than 0.01, getting that out of the absolute value. Remember those rules of absolute value we had? Or 3.99 is less than x squared is less than 4.01. Take the square root of both sides, or all three parts here. We get the square root of 3.99 is less than x is less than the square root of 4.01. And then we can subtract 2. So the square root of 3.99 minus 2 is less than x minus 2 is less than the square root of 4.01 minus 2. And at this point, we would see whichever one of these is smaller in absolute value. We consider the absolute value of the square root of 3.99 minus 2 and the absolute value of the square root of 4.01 minus 2, and that would be my delta. We would have consider these, and whichever is smaller, delta, oops, that's a lousy delta. Delta would be the min of these, whichever one of these. Okay? The idea being we want the smaller of those two because I need the entire interval to work. If I have, more than likely this is not quite symmetrical, and so you need the smaller one so that, for example, let's suppose that the downside is a smaller one, then when I bring that up, the entire interval gets mapped in to where we want. Whereas if I pick the larger one, then it would map too large down here. It wouldn't work. We would be outside the interval that I care about. And so my picture is a little off. This should be up here. And so we're mapping now completely inside the interval. If I had chosen the bigger one, then it would have worked on the top end, but it would have put me outside the epsilon interval. And so that's why we need the smaller of the two. Okay, so this is the idea of the epsilon delta definition.